Hello everybody, this is Miss Pikarski. I am out at a professional development thing and you guys have a sub. Hopefully you guys are all behaving yourselves. You are going to be responsible for the material I go over in this video, so make sure you are following along. So put the phones away and take notes, and I really want you working along while I'm doing this in the video. If you need the substitute to pause the video so you can work through a problem, go ahead and ask the sub to do so. All right, let's go ahead and get started. So yesterday we were finishing up all of our, looking at our polynomials and figuring out all of this stuff with the polynomials. And one of the problems we looked at yesterday was an equation that looked like this. And I wanted to talk about the relationship between double roots of a polynomial and the relative maximum and minimum values. Okay, so notice that the equation has x times x minus 1 squared times x plus 2 squared. And we have x-intercepts right here at -2, at 0, and at +1. Okay, and this x is giving me a x-intercept right here, or at 0. This factor here is giving me the x-intercepts at +1, and then this factor here is giving me the x-intercepts at 2. Okay, so hopefully you figured out by now that, or you recall that the factors in our polynomial, we set each one of those equal to 0, and you solve for x and you get your solution, or your 0 or x-intercept, or whichever one term you want to call them. Okay, so if you set this factor equal to 0, it's just x equals 0. If you set this one equal to 0, it looks a little bit complicated because you have x minus 1 squared equals 0. And you would have to square root this, and the square root of 0 is 0, and then you add 1 to both sides, and so on. Same thing for this factor. Okay, so basically what we're talking about when we talk about double roots is, notice how you have the squared term here and the squared term here. What that means is that on your graph, or how it will look on the graph, is instead of hitting the x-axis and just crossing through it, you hit the x-axis and then bounce off. Anytime you have a double root here, you would hit the x-axis and bounce off. Now, let me rephrase. It's called a double root because typically you'll see squares. You're not often going to see x plus 2. Let me delete that. 2. You won't typically see a factor where it's like raised to the 4th power, the 6th power, the 8th power. But anytime your exponent is an even number, then it's going to hit the x-axis and bounce off. If it's an odd number, like if we had x to the 3rd power, it would still cross the axis like this one does here. So odd exponents cross axes, and even exponents hit the x-axis and bounce off. Okay, that's a good thing to remember, because a lot of times when we get to our more complicated polynomials, you'll have multiple double roots. Okay, so let's go ahead and look at some of the work that we're going to do today. Some of this is kind of a review, making sure you remember the traits about end behaviors and leading coefficients and your highest degree. So on this page we have two graphs. We have this graph here and this graph here, and we need to figure out which of these equations match the graphs just based on what we know about polynomials. Okay, so this equation here has to be an odd degree polynomial because we are we're going in different directions. The end values are going in different directions. So this one is out, this one's out, this one's out, this one's out, and this one is out. The only option we have is C, because that's the only one with your highest degree is an odd number. Okay, so for this graph, f of x, the answer is C, because that's the only one that's odd. And we only had to use the fact that the n values were going in opposite directions to figure that out. All right, now let's look at this one. We have graph G. Now both ends are going in the same direction, so it has to be an even exponent. So now we can cross this one off. Also notice that the right side is going up, so the leading coefficient has to be positive, so we can cancel out that one and that one. Our y-intercept is at 2, so our constant term has to be a 2. Our constant term is the number on the end, remember, so this is a 2 here, a 2 there. All right, so now we need to look at our degrees. If my exponent is an 8, then I should have at least, or I can have as many as 7 bumps. Or turning points. Let me see if I have the right number. 1, 2, 3, 4, 5, 6, 7. Oh, I drew it too many times. So 1, 2, 3, 4, 5, 6, 7. Yeah. So if my exponent or my degree is an 8, then my graph should look more like this instead of this. So according to all of those characteristics of polynomials, it's a safe bet that D is the correct answer. All right, so now I just want to remind you of some of the things that you guys learned in Algebra 1 and Algebra 2 about your finding x-intercepts and y-intercepts and end behaviors of the graph. On this one, we just have a linear equation, and the constant term is our y-intercept, so I'm going to put a dot when x equals 3, and with the y-intercept, or sorry, with the linear equation, your slope is 1 here because we don't have any numbers there. So our graph would look something like this. Let me do a line. It's much easier. Okay. That's not the shape that I wanted. Dang it. There we go. So our graph would go something like this. Okay, use your student IDs to give yourself a straight line there. All right, let's look at this one now. We have this ends up being a quadratic equation. If I would FOIL that or box it, I would get a polynomial in standard form. Let's see, x squared minus 25, right? That's a difference of squares there. Now, the reason why they have it set up in factored form is to help us find their x-intercepts. So if I set this factor equal to 0 and solve for x, I would get x equals -5. So I'm going to have an x-intercept at -5. And if I set this equal to 0 and solve for x, I would get x equals 5. So I will have an x-intercept at -5 and +5. Okay? Now notice that our leading coefficients are positive numbers, so our n values have to be going up. So this is what's going to look like, and I honestly have no idea where exactly where the graph is going to look, or what the graph is going to look like on the bottom. But if my x's are zeros, then I can find my y-intercept. So if x is 0, 0 squared is just 0, so I'm left with -25. So if each of these tick marks here was 5 units, so 1, 5, 10, 15, 20, 25, so then my y-intercept would be right here, and then these would connect. Wow, I'm actually kind of impressed with how well I was able to draw that line. All right. something like that. Doesn't look absolutely fabulous, but my graph would look something like this. Okay. Now for C, same kind of thing. You're setting each of these factors equal to 0 and figuring out your x-intercepts. So this one would give me an x-intercept at -4, so right here. And then this one would give me an x-intercept at +4 right here. And then this one gives me an x-intercept at -1. Notice that with each of my factors, if I just change the sign, it tells me where my x-intercept is. All right, and then I'm not going to bother foiling this to figure out what I get. I can just plug zeros in for all my x's and multiply everything together. So I would have 4 times -4, which gives me -16, times 1, which is still -16. And let me see if I have 1, 2, 3, 4, 5, 6, 7, 8. Nope, so I think each of these tick marks should count as 2. So that would be approximately -16. And now I need to figure out what type of degree this is. Well, notice if I multiply all my x's together, I get x to the 3rd power, which ends up being an odd degree. And my leading coefficient is positive. I have a +1 over here. So my left side, or excuse me, so my right side is going to be going up because the leading coefficient is positive, and the left side is going to be going down because it's an odd degree. I know that I'm going to have a y-intercept all the way down here, and it's probably a little bit more curvy than what I have, and then somehow I'm going to have a connection here. And I don't know how high up my this part of the graph goes. It could go really high up like this, or it could go kind of more shallow like that. I don't know, but I know that somewhere over here I need to get these 2 points connected like that, okay? So with our polynomials in factored form, it's really easy to graph them and see what they look like. All right, so I want you to go ahead and do this one on your own, and when I check your work on Monday, I will be checking to see if you have this one graphed. Remember to set each of these equal to 0 and solve for x to find your x-intercepts. Plug in zeros for x to figure out what your y-intercept would be. You should be able to do that one fairly easy. Try to do it without a calculator. Okay. All right, so now moving on. What we're going to be doing now is I'm going to go through different methods of factoring your polynomials so it's easier to graph by hand without needing a calculator. Okay. This is a skill that you will see again. You saw it a lot in Algebra 2. You'll see it again in college algebra and college pre-cal. And then when you grow up and have kids, your kids will need you to help them with it. This factoring is not going to go away. All right, so let's look at this. In this one for A, it's a fairly easy factor. We just need to find factors of 20 that when I subtract them from each other, I get a -1. So I can use 1 and 20, 2 and 10, or 4 and 5. Well, if you set up the factors to be 4 and 5, then you can subtract the 5 from the 4, and you get -1 in the middle. So with our factors, one would be x minus 5, and one would be x plus 4. So then when you set these equal to 0 and solve for x, you get x is 5 and -4. So if you had to graph this, you would put x-intercepts at 5 and -4. Okay, so let's look at this one. This one looks a little bit more difficult, and some of you are totally freaking out. And usually I would have said use your quadratic formula for this because I like the quadratic formula. You can use it. It's a fail-safe process, but I know a lot of you guys just absolutely hate the quadratic formula. I'm going to show you another method of how you can do this. It's called the slip and slide method. And the process with the slip and slide method is taking this 2 and sliding it over to the 18. So what you're going to do is you're going to say 2 times 18. Well, 2 times 18, I think, is 36, right? So now, instead of trying to find all the factors, you just need to find the factors of 36. So we just rewrote the equation so that I don't have my leading coefficient anymore. I slid it over here, okay? And I want two numbers that I can, and obviously this is a negative, so one of these factors will be positive and one will be negative, and they need to combine to give me a -9. So let's see. 1 and 36 won't work. 2 and, not 2, 3. 3 and 12 would give me a 9. Okay, so the factors that I'm going to use are 3 and 12. 3 times 12 is 36. 3 minus 12 gives me a -9. So I'm going to set up my factors to be x minus 12 and x plus 3. Okay, at this point, we need to slide the 2, remember this 2, our leading coefficient? We're going to divide both of our factors by 2 since we slid our 2 over here. We're trying to slide it back, and to slide it back we have to divide both of our terms here by 2. And then at this point I can simplify the fraction, or I can multiply both terms in the factor by my denominator. So here x minus 12 over 2 is just x minus 6, and here x plus 3 over 2, I can multiply the x and the 3 halves by 2, and I get this 2x plus 3. Okay, whoops, I almost messed that up. I did mess that up. There we go. All right, so hopefully, I know this for most of you, you may have seen this process of slipping and sliding before. Some of you may have never seen it. If you need to see it again, go onto YouTube and search for videos with the topic of solving quadratics by slip and slide method. Okay, that's the process that I just showed you, is solving quadratics by the slip and slide method, this method. Okay, I think if you watch a couple of YouTube videos on the process and work through the examples that are in the videos, it'll help you understand how to do this. It's a fun and simple way to do it for those of you that are absolutely terrified of the quadratic formula. All right, now once we set each factor equal to 0 and solve for x, we get x can equal 6 and -3 over 2. And that's where we would put our x-intercepts for this graph. All right. For C and D, these ones are a little bit easier polynomial functions. And we can just solve for x. So because our x is negative here, I'm going to move it to the right side. I'm going to set the equations equal to 0 and solve for x. So I move that to the right side and I get x squared equals 25. Well, most of you know that you need to square root that, and that the square root of 25 is 5. But most of you, and hopefully most of you, remember that anytime you take the square root of any number, the answer is both positive and -5. So with this graph, you should put an x-intercept at -5 and +5. Okay, here's another example, slightly different. This time, instead of having a minus x, we have a -5. And I'm going to add 5 to both sides, so I get x squared equals 5. And then, of course, I'm square rooting again. And again, we have both positive and negative answers. And I know some of you are right now typing in the square root of 5 in your calculator to find the rounded answer. If you are trying to figure out approximately where to plot these on your graph, go ahead and do so. Find out what is the square root of 5. Honestly, I don't have it memorized in my head. I would have to plug it into the calculator as well. And we get the square root of 5 is 2.23. So if I was plotting this on a graph, I would find a value just a little past 2 and put a dot there. Okay, however, if I'm asking for the solutions, I don't want you to tell me 2.2. I want you to tell me the square root of 5, positive or negative square root of 5. Okay, let's look at some more examples. Now, these ones, I know you can probably factor by yourself without using the quadratic formula, but you will have some graphs or some polynomials where you'll have to use the quadratic formula. So I'm showing you, reviewing with you again. I know you've seen this a million times in Algebra 2. Essentially, you have your polynomial. This only works when you have quadratic polynomials. So your highest degree is a 2. And so you have your leading coefficient is your a value. The next x is your b value, and then the constant term is your c value. And you would take those values, your a, b, and c, and rearrange it into an equation that looks like this. And then, of course, you would have to simplify it. Okay, so if this was our equation and we wanted to use our quadratic formula to solve it, we would set it up like this. Notice that because this 2 is negative, I have a negative 2. And notice I also have a negative here, but it's in the parentheses. And then my minus 3, I include the negative over here as well. Now, when I first start simplifying this, I'm going to take it step by step. Guys, I really need you to do this step by step because I find when people just plug it into the calculator, things mess up. Especially since I always at this point get somebody that says, hey, Miss Pi, where's the plus and minus sign on the calculator? You can't. You have to plug this in separately, and I will show you in a minute. So first, all we're doing is simplifying everything. So the negative 2 becomes a positive 2. This becomes 4, and this here combines to give you 12. And then you can simplify that further with 2 plus or minus the square root of 16 over 2. If you take the square root of 16, why did I put it down there again? I don't know why. If you take the square root of 16, you get 4. At this point, you have to separate the fractions, okay? So you're going to have 2 plus 4 over 2, and you'll have 2 minus 4 over 2. Don't forget, you're going to have a plus sign once and a minus sign once. Okay, when you simplify all this, you end up with a 3. When you simplify all this, you end up with negative 1. So your x-intercepts are at 3 and negative 1. And guys, you can graph this and you can see that I have an x-intercept at negative 1 and at 3. Okay. Coincidentally, when you guys are looking for your factors and your solutions, anytime you can graph it and you have whole number solutions, go ahead and use those. Okay. All right. There was a hint, a foreshadowing of something we're going to be doing on Monday. All right, let's do the quadratic formula with one more equation. I know you guys are dying because most of you are like, Miss Pi, this one is super easy to factor on your own. I want you to get practice with using your quadratic formulas. You will be using them next week. So practice with the easier problems to make sure you've got this. All right, so we'll set it up again. A this time is, this time A is 1, B is positive 10, and C is 25. When we set up all that stuff in our quadratic equation, it looks like this, and we can simplify it, and we get this. And most of you have figured out that 100 minus 100 is 0, and the square root of 0 is 0. Okay? And so you end up with negative 10 over 2. And usually we have 2 x-intercepts. But this time, oops, I forgot the negative sign over here. Hold on, let me put that negative sign back there. Do not drop the negative sign. That should be a negative 5. Okay? And then, again, so this, we should have 2 x-intercepts, but if you look at it, we just have 1 x-intercept, but this is a double root where it's hitting the x-axis, and instead of crossing through it, it's bouncing off, okay? Okay, so here's another one. This time, if you don't notice that my exponent is a 4, not a 2, so I can't use the quadratic formula. I can still go ahead and set this equal to 0 and solve. When I do that, I get x raised to the 4th power equals 81. And then most of you figured out that you can just do the 4th root of 81, which ends up being positive or negative 3. Remember that anytime you take an even-rooted radical, it can be both positive or negative. And then if you look at the graph, you can graph this and you can see that you have an x-intercept at negative 3 and at positive 3, and that you have right here initially you might say, hey, we only have 2 solutions. And so far, whatever our exponent is, our degree is here, that's how many solutions we should have. On either Monday or Tuesday next week, I will explain where those other solutions went. Some of you may already know about them, but we'll wait until next week to discuss them. All right, let's look at this one. And again, some of you may be able to factor this without using your quadratic formula. And we have, oh, sorry, I forgot. Notice that we have 3 here, x to the 2 power or squared, and then an x. And your greatest common factor between all these is an x. So we can just factor out an x, and when we do that, we get x times this quadratic formula. Well, I can factor this quadratic formula by figuring out what 2 numbers to add or subtract from each other to get a positive 2, and which multiply together to give me 8. So 4 times 2 gives me 8. And if I have a positive 4 and a negative 2, it ends up being, I combine those and I get positive 2x. So I'll have an x plus 4 and an x minus 2. When I set all those factors equal to 0 and solve for x, I get x equals 0, negative 4, and positive 2. And I can check by graphing that, and I see that I have an x-intercept at negative 4, 0, and positive 2. Okay? Let's see. How many more factors do we have? Just a couple more. All right. Oh. No. That's not what I want. This is what I want. All right. Find the real zeros of the following polynomials. I feel like I've been doing this forever. Okay, basically I'm factoring. Again, this time set it equal to 0, and I start solving for x, and I get x to the 3rd equals 27. And then I can just take the cube root of 27. And notice this time my answer is only 3. The reason why is because if my x is negative 3, it doesn't give me the same results. I don't end up with an x-intercept there. So when you have radicals with an even number here, then your answer is both positive or negative. If it's an odd root, then it's just positive. Okay? All right, let's look at this one. Set it equal to 0. We have negative 127. Or excuse me, 125, and when I take the 3rd root of negative 125, I end up with a negative 5. The reason why is because this negative follows, okay? So essentially, I think I misspoke over here. If your number here is positive, then this number has to be positive. If this number is negative, this number has to be negative. Anytime your radicals are at a power that's an odd number. All right, let's look at this one. It says use your calculator to find the real zeros of this equation. I will tell you in some of this page I am skipping some of the problems for now, and I'll look back. We'll go over them later on. Okay, so we have this polynomial. I plug it into the calculator, and I analyze my graph. Hopefully most of you remember how to analyze your graph. The steps to analyzing your graph are going to menu, analyze graph, and these are called zeros. So you're looking for your 0. Okay. Anytime you have to analyze your graph, and if your x-intercepts look like they're on your tick marks, you can just pull up your table to find the x-intercepts. But when they're not on the tick marks, go ahead and analyze your graph, menu, analyze graph, and you're looking for zeros, and you'll have to do lower bound and upper bound to find each of your x-intercepts, okay? Notice that this one over here is so close to the line that they don't even give us a 0 here. But if you wrote that out, and rounded to even the 10th decimal place, or no, not the 10th decimal, the 9th decimal place, it would still round to 0. So we're going to consider this an x-intercept. Hopefully you guys know how to analyze your graph and do this. This isn't just another way, another tool to find our x-intercepts. Factor and finding the zeros of each function. Trying to remember what page this is on. I actually do not know, but if you have all the pages out from yesterday, then you'll have this information. Find this problem on one of your pages. Okay, so this is something I like to call grouping. Okay, one thing that we can do is I can group these two terms and these two terms. And all I'm doing is separating them by putting parentheses around them. And then I want to look at this term and see what is my greatest common factor. And I see that I can factor out an x squared between this term and this term. They both have an x squared in it. When I factor that out, I get 3x minus 2. Now when I do the same thing to this term, I have 12x minus 8, and I can factor out a 4. Both of them are divisible by 4, and I get a 3x minus 2. Because this factor and this factor are the same, then I can take the x squared plus the 4 and set that as a factor and multiply that by 3x minus 2. You may not have ever seen this done in your Algebra 2 class, but you can do that. And I'm going to go over a couple more examples of how to do this. And so again, we'll set both of our factors equal to 0. And then we solve for x on both of them. Now this one we just get x is equal to 2/3. But over here we still have to do some stuff to find our answer. And so we have plus or minus the square root of a -4. And most of you probably know, or you remember from Algebra 2, that anytime you have a negative sign here, you can take it out and with an I. That stands for imaginary solution. And then the square root of 4 is just 2. So the answers would be positive 2i and negative 2i and 2/3. Okay. Let's look at another example where we're grouping. Now notice that your exponents are not put in the correct order, or your variables are not in the correct order. It should be 2x to the third first, then x squared, then 8x, and then 4 at the very end. Okay, so make sure you put them in the right order and go ahead and group them. And again, you'll see that this grouping is very similar to the last one, where we take the first two terms and the last two terms. And again, this one you have x squared, but this time the term in the parentheses is 2x plus 1 when I take an x squared out of both of those. And here I can factor out a 4, and I get 2x plus 1 in both. So one of my factors is 2x plus 1, and the other one is x squared plus 4 here. And then I set both factors equal to 0. And then I start solving for x. And on here I get x is equal to -1/2. So I have an x-intercept at 1/2. And over here I have a -4. And the square root and all of that is so similar to a. Okay. I know I'm going through this fairly quickly, but hopefully you'll be able to get it. We will have some more examples like this in the future. Let's look at C again. Notice that we are not grouping these, but we're just getting our greatest common factor, which is x squared. And when I pull out an x squared from each of these, the x to the fourth becomes x squared, and x to the third becomes x, and then the 20x squared is just going to be 20. And now I have a quadratic here, and we've seen this one before. Okay. When I set each of these equal to 0 and solve for x, I get x equals 0 and -4 and +5. And because this here is squared, then I have a double root at 0. So instead of passing through it, it's going to hit 0 and bounce off. Okay, let's look at a couple more examples. So greatest common factor right here is a 4. When I factor that out, I get this. And notice that we have a square term here, and our middle term, sorry, a fourth raised to the fourth power here, and our middle term is squared. So both of my factors are going to have x squared in them. And then I need two numbers that multiply together to get a 2 and add together to get 3. So my numbers are +2 and 1. And I set those factors equal to 0 and solve for x, and I get x squared equals -2 and x squared equals -1. And I square root. And here, I square root these, and I get the square root of -2 and the square root of -1. This is as simple as I can make it. I cannot simplify it anymore, but the square root of 1 is just, the square root of -1 is plus or minus I. We are going to have a lot of solutions with i's in them. Okay, last thing I want to go over is called the rational root theorem. It states that if a polynomial, you know what, I'll let you guys read this while I get a drink. Go ahead and read it. I'm getting a drink. So we're setting up a fraction with, in the numerator, you're going to take all of your constant terms. Notice it says P is factors of a sub 0. A sub 0 is your constant term here, and Q is the factors of a sub n, and that's your leading coefficient. So the number that is your constant term goes in the numerator, so the 12 goes in the numerator, and the 4, which is your constant term, goes in the denominator. Okay, and I believe you'll have to go back a couple pages to find these problems. So we have 12 in the numerator, 4 in the denominator. For these numbers, you need to figure out all the factors of 12. So 1 and 12 gives you 12. 2 and 6 gives you 12. And then 3 and 4 give you 12. So those are all the numbers that you can multiply together to get 12. And notice how I put them in numerical order. And then all the numbers that will give you 4 are 1 and 2 and 4. Okay, at this point you have to figure out all the different possible outcomes where if you divide each of these terms up here by 1, you get 1, 2, 3, 4, 6, and 12. And then if you divide each of these terms by 2, you end up with 1/2. 2 over 2 becomes a 1, so we don't need to rewrite that. 3 over 2 is a new one, 3 over 2. 4 over 2 is 2. We don't need to write that. 6 over 2 is 3. And 12 over 2 is 6. All of those terms are still there. And then we have 1 over 4, which is a new term. And then 3 over 4. And then all the other terms we already have written there. So basically what this is saying is it's figuring out all the possible rational roots of a polynomial. So rational roots can be fractions or whole numbers. So notice these fractions here or the whole numbers. It cannot be a radical like the square root of 2. Let me move that out of the way. Okay, it cannot be a radical like the square root of 2 because that's a number that keeps on going forever. It doesn't stop. It has to be a number where it will stop. Okay, so that's what the rational root theorem is. We just did 16 and 17 and 19 to see if we can figure out all the possible x-intercepts. Okay. So we have here in the numerator we have an 18. Actually, no, we don't have an 18. We have a 9. Again, our terms are not in the correct order. So Our leading coefficient is a 2, and our constant term is 9. So we should have a 9 in the denominator, or excuse me, 9 in the numerator. Oh, that's what I did. I wrote it in the correct order. So my constant term is 9, and we have a 9 in the numerator and a 2 in the denominator. And then all the factors of 9 are 1, 3, and 9. And then all the factors of 2 are 1 and 2. And if I divide each of those by 1, I get 1, 3, and 9. If I divide each of them by 2, I get 1 half, 3 halves, and 9 over 2. And 9 halves? 9 halves. All right, let me delete these real quick. So that's essentially all we're doing here is figuring out the possible x-intercepts. We're not saying we have an x-intercept in each of those locations. Those are just the possible ones that are whole numbers. Now, don't forget that these can be negative or positive, okay? All right, last one, and then I think we'll call it a night. My leading coefficient's a 2, so that's in my denominator. And my constant term is a 16, so that's in my numerator. All the factors of 16 are 1, 2, 4, 8, and 16. The factors of 2 are just 1 and 2. If I divide everything by 1, I get 1, 2, 4, 8, and 16. If I divide things by 2, I get 1 half. And that is the only one that will be a new number. So these are all the possible x-intercepts, okay? And now, I will see you on Monday where we will start using our possible x-intercepts and our synthetic division to find out which ones actually do work and to start reducing our polynomials to something that's more manageable. All right, so I will see you Monday. Bye.